Good evening, students. Welcome to yet another lecture of practitioners' approach in descriptive, predictive and prescriptive analytics. And we have been looking at different aspects of analytics, and we are building the foundation and growing up upon which we can actually learn bigger tools and important tools. And today we are going to discuss one of the most important concepts in the analytics, which is called as a normal distribution. You might remember that in the previous class, in an earlier class, we have gone through the probability, then probability density function, continuous cumulative density functions and extra like that. But today what we are going to talk about it is more from how do you look at the normal distribution, which is the cornerstone of many of the analytics tools from a practitioner's viewpoint. So let's first talk about histograms. We already talked about what's a histogram. And we have also defined that histogram is a pictorial representation of the frequency distribution. So, if histogram is really nothing more than a bar chart used to chart quantitative data. So, you have quantitative data and you are trying to chart. So, in another way it is a pictorial representation of the frequency distribution. And the frequency distribution is which groups data into classes. We have seen this in the earlier lecture. So, histogram is a pictorial representation of the frequency distribution which groups data into classes. The quantitative data is put it into classes. So, we had already seen this data, this lunch data. We have been taken lunchtime of coworkers data. We have already seen there are 12 data values 1, 2, 3, 4, this is 1, 2, 3 all the way up to 11, 12 and there are 3 rows like this, and so we have 12 times 3, 36 data values are part of this. Remember we try to talk about how many classes and other things, but let us create a frequency distribution with a class width of 5. Class width of 5 means you can think about starting it as 30 to 35 or actually 30 to 34 if you think about it, 30, so it will be 30, 31, 32, 33, 34, 4, then 35 to 39 like this, okay, that type of a classes, okay. And let us then count, using the counts on the frequency distribution, we will create a histogram and let us see what is the shape of the histogram, let us see how does a histogram look like, okay. So, if we take a look into the data, you can see that this is the 30 to 34, okay. And then this is 35 to 39, 40 to 44, then 45 to 49 like this. Remember this is one of the reasons why I earlier told that class marks can be used. Class marks are recommended instead of class intervals, okay. So, you can see here as 30 to 34, instead of that you can basically represent it as 32, okay, which will actually is the class mark for this particular class rather than trying to do this interval, okay. So, you can see that the 30 to 34 interval you have 1 data point, 35 to 20 you have 2, then you have 3, then you have 4, 5, 6, then you have again 5, 4, 3, 2 and 1, okay. So, you have 1 value here, there are 2 values, there are 3 here, 4 observations, there are 5 observations, there are 6 observations, then there are 5, then there are 4, then there are 3, and there are 2 and 1, okay. So, when you think about a histogram like this, when you plot a histogram like this, because this is a unique set of data, so it actually looks very nicely. But when you have a system like this, if you plot the data values from a relatively large sample or population, the data forms a mount, okay, or a bell shaped curve or bell shaped distribution clustered around the center of the data set, which is called as a normal distribution. So, what we are saying is that it forms a mount, okay, this is the mount that we are talking about, the mount, okay, and it forms a, if you think about it, it is kind of, this is what we call as the bell shaped, okay, this is the bell shaped and this is the cluster around the center. Okay. So, that type of a distribution where you have going down tails and a particular curve where there is a hump or a mound at the middle of the data, which most of the data values are clustered around it. So, that type of a data set is supposed to be said as something that data is coming from the normal distribution. Okay. So, why is normal distribution important? The fundamental question is why we like normal distribution, or why statisticians fall in love with normal distribution. The big reason is in normally distributed data sets, the mean is the x bar, median x tilde, and mode is the most common occurring value. Okay. They are all equal. Okay. So, the central tendency of the data is lying around the mean, median and the mode. Mean is the average, mean implies sample average counted by sigma xi over n. Okay. X tilde, median, is the midpoint of the data. So, the x bar, which is the mean, x bar, x tilde and the mode, they are all equal, and other values, okay, the values that are other than this mean, median and mode, they are symmetrically distributed around the center. So, it is also a well behaved system. Okay. So, that is why the other values that are distributed symmetrically around the center, where the mean, median and the mode are equal. Having normal distribution of the data set usually allows the use of parametric stats to analyze the data. So, if your data is normally distributed, parametric statistics is possible. I mean, what parametric stats means is you can use the parameters that are taken from the data like the mean, standard deviation, etc., to form conclusions about the data. If you can form conclusion about the data, that means you can form conclusion about the process from which the data came in, process from data. Okay. You can do that. If it is not normally distributed, if the normal distribution is not possible, then we use what we call as non-parametric statistics. But parametric statistics, there are quite a lot of tools and it is quite well developed system. So, if you can get normal distribution, it makes our analysis or analytics life quite easy. Okay. So, refining what we have said before, use of parametric statistics is based on the quantitative data that are normally distributed. Okay. So, if the data is normally distributed, quantitative data, numerical data that are normally distributed data, then you can use parametric statistics. So, another practical rule, this is a practical insight, is even if the data is not perfectly normal, if the curve is not like this, if it is not like the perfect bell shaped curve, it could be, so if you draw the histogram, it could look something like this. If you see the histogram like this, okay, it is not really perfectly shaped normal, but you can still see there is a hump and stuff like that, and most of the values are around the center, stuff like that. The inferential statistics or our parametric statistics is powerful enough to allow some flexibility, or it allows for some of those deviations in the data. So, even if you have a not so perfect normality in data, you can still use parametric statistics. Okay. Now, what are the things that affects the look of the distribution or the way the normal distribution looks? The first factor that affects it is called as the skewness of the distribution. Okay. And the skewness means that the data distribution is stretched out to one side or the other more than what is expected from a normal distribution. So, what we said about the normal distribution was that normal distribution is symmetric around the middle value, right. The mean, median, mode are exactly the same, and then it is symmetrically distributed with most of the values clustering around the mean. That is what we talked about. Okay. So, an ideal normal distribution is symmetric around the middle value, which is typically the mean. But if the distribution is moved to one side or the other, if it is more to one side than the other, then we can say that the distribution is stretched out. For example, if the distribution is something like this, then it can be told as a skewed distribution. Okay. So, the skewness is a measure of the symmetricity of the distribution. So, when we have more values that are greater than the mean. Okay. So, if you take an example, if this is the mean, the center line is the mean, if you have more values that are greater than the mean, that means the values are to this side, okay, this side more than the greater to the mean, then the distribution is said to be positively skewed or skewed to the right. Okay. So, a distribution that has a shape like this, more values to the mean, this can be called as a positively skewed distribution, okay, or more values to the right side of mean. Okay. Now, when we have more values than expected less than the mean, okay, or which is said that it is negatively skewed or skewed to the left. So, same way, if you have a distribution where it is something like this, where this is the mean, in both cases this is the mean, but more values are to the left side of the mean, this is the left side of the mean, then this is called as a negatively skewed, okay, or skewed to the left side. So, the values that are less than the mean will give you a left skew, values that are greater than the mean will give you a right skew or the positive skew. So, to illustrate this example or to illustrate this concept, let us add the values 90, 90, 90, 3 90s and 100 and 100, 200s and a 105 to the lunchtime data, which was in the previous example that we talked about. This is the lunchtime data. So, what we are doing here is we are adding values of 90, 90, 90, 100, 100 and 105. So, you are done 1, 2, 3, 4, 5, 6 more data points are added. So, now you have 42 data sets. Okay. When you add that much of values to this and then you go back and let us plot the histogram again. Okay. We do the histogram with the same 5. So, this is the 32, 34, 35 to 39, 40 to 44 like this. Okay. And we do this histogram and you can see that obviously yes, in 90 to 94, 95 to 99, 100 to 105, 105 to 109 kind of a thing, you can see that there is more observations, it is not perfectly symmetrical, you have more to the right side or greater than mean. The average value would probably be somewhere here. So, there is more observations to this side. So, this kind of a histogram which kind of creates something, you can call it as like a longer tail. It is not symmetric, but it actually creates this one. So, this is a skewness. Okay. So, this is a skewed normal distribution in this regard. The other one is a concept that we talk about it as the kurtosis. Okay. One thing what we talk about is a skewness where it is talks about the symmetricity of this. The kurtosis on the other hand, kurtosis it refers to the problems where the data distribution okay, that cause it looks like either more peaked out or more spread out than what would we expect in a normal distribution. So, what happens is you might assume that the normal distribution is something symmetric like this, okay. But instead of this distribution, you could think about a scenario where it could come more peaked like this, okay. You can think about a scenario like this, more peaked, or you could think about another scenario where it is more flat like this, okay. Anyway, this is slightly should be more peaking than this, but anyway my normal distribution drawing skills are quite bad. So, this can be like a larger peak, this is a flat peak, okay. So, this is where it's more spread out, okay, where this is more peaked up, okay. When there are more values than expected, when there are more values than expected at both ends of the distribution will flat out. So, when there are more values at the ends, then it will flatten out. This results in a scenario called as kurtosis, okay. So, this is plane, kurtosis becomes planar, okay. So, this is the kurtosis, okay. When there are more values than expected at the center of the observations, the reverse is true. If more observations are found in the center of the observations of the data set than expected, it causes the distribution to appear more peaked than it would be, resulting in a leptokurtosis. So, this is what is called as a leptokurtosis, where you find more than expected observations at the center of the data or near the center of the data, okay. All right. Now, the other part is that the area under the normal curve, okay, which is because as I said the normal distribution is a symmetric distribution and people like normal distribution because it's the mean, median and the mode are exactly the same values and the spread is also quite symmetric. So, things that are symmetric are easy to estimate. So, normal distribution, by if you are to describe the normal distribution, it is ideally described by its mean, the average and the standard deviation, okay. So, the mean is typically denoted by the letter mu and the standard deviation is denoted by the Greek letter sigma, okay. So, the ideally speaking the normal distribution says that about 34.1 plus 34.1, which basically gives you 68.2% of data values, okay. They will lie within this one standard deviation of the mean, that is one observation of the normal distribution. So, now you have 13.6 and 13.6, 13.6, 13.6, that is 2, 6, 7, 27. So, 27.2 percentage more gets added to the 68.2. So, that is 4, 15. So, 95.4% somewhere here, okay. 95.4% will lie between the two standard deviations and then 99.8 percentage will lie between the 3 standard deviations, okay. This is what the 2.1 and 2.1, 2.1 will get added together is 2, 4.2. So, if we add 4.2 with this, then you will get it as 6, 9, 9, 99.6% of the data will fall within the 3 standard deviation, 99.6% of the data, okay. So, but the issue here is that for each data set you will have its own mean and standard deviation. So, for different set of normally distributed data, it is quite hard to compute the probabilities, okay, which is given by the area under the curve. So, if you have one set of data, you will calculate the mu, you will calculate the standard deviation and from there you will create the curve. Once the mean and the standard deviation changes, you have to draw a new curve. So, to avoid that, what we do is we use a standard normal distribution with a mean of 0 and a standard deviation of 1, okay. So, what we do is we have a reference distribution with a mean of 0, this mu is equal to 0, okay. This is one case and standard deviation equal to 1, which is sigma is equal to 1. This is the say this is called as the standard normal distribution. So, if we call this as a random variable x, sorry, not x bar, x, okay. X is a random variable, x is a normally distributed random variable mu and sigma as parameters mu and sigma, then z is a standard normal distribution, is distributed normal with 0 and 1, the mean and sigma being 0 and 1. So, the random variable z is denoted for z, E is denoted for standard normal distribution. And the question obviously is that, I mean, why is it so hard to find the area under the normal probabilities, okay, or why is it hard to find the area under the normal distribution? Because normal distribution, number one, is a continuous probability distribution, and the probability density function is given by this ugly looking equation, sigma times 1 by root of 2 pi e to the power of whatever it is, okay. So, for any given range, as we suggested earlier, the CDF, okay, if you want to find probability of x less than or equal to little x, it was given by minus infinity to x f of x dx. This is what our CDF was, cumulative density function was. So, in this case what happens is we have to keep on integrating this function for all different set of values to find this, okay. So, you keep on integrating, and so when you draw this curve, all you are doing is you are integrating it at many places, and these integrals get added to get the final curve. So, hence what we do is, instead of doing this, we use a standard probability table, okay, and then from there you calculate the value, otherwise you use the normal distribution function in Excel to calculate the normal probability. Either you use a table to check it if you are doing it manually, or use the norm distribution function from the Excel to find the probability values. Right. So, the standard normal distribution tables are shown here. So, what happens here is there are two parts, one is the left side of the mean, the other is the right side of the mean, okay, the positive values. So, if you look at here, you can see that, you know, minus 0.009 is 4.61, and you can see exactly the 0.00 value is 0.5, the middle value. So, this is the left of mean and this is the right of mean, okay, and you can say that these values actually tally between. So, this is the so when you say what is 3.0 is 0.9, see, you can see that this is about the 3.0, this is the 3 standard deviation, right, and if you look at the minus 3, it will be right here, okay, minus 0.13. So, it will be 99.7% will be exactly what we will talk about, okay. So, one simple example that we will try to say is that a study suggests that the average height of a male in United States is 69 inches and the standard deviation is 3 inches. The data follows normal distribution. Find the probability that any given person will fall within a height of 65 inches to 75 inches. So, what we are talking about is there is a normal distribution, okay, something like this, with the average being 69 inches. This is the 69 inches, the average height, okay, and the standard deviation is the sigma equal to 3 inches. And what we are asked to find is what is the probability that the height of the person will be between 65 to 75 inches. This is 75 inches, this is 65 inches. So, to find that, what do we do is we find first this area and then we find this total area and then we subtract both these areas. So, to do this on one way to do it is you can use Excel and find norm dist of 75 with mean of 69 and standard deviation of 3, and same way norm distribution of 65 with mean of 69 and 3. What is the probability? You will get the P1 and you get the P2. This is the cumulative probabilities, and so P1 minus P2 will give you the resultant probability. Other option for us to do it is we convert this into the standard normal curve, what we call as z is equal to x minus mu divided by sigma, okay. So, what we are giving here is the x is the value that we want, which is 65, the mu is the average, which is 69, and sigma is 3, okay. So, 65 minus 69, that will be minus 4 divided by 3, 4 by 3 will be minus 1.30, that is 1. Be 40, right? That's okay. 1.3. Okay. So we go back to the table. You can see that minus 1. This is minus 1.0. Okay. 1.3 will be this value. Okay. 0.1515. Okay. 1. Sorry, not 1.03. My bad. Sorry, I gave you the wrong idea. 1.30, that's what we want. I mean, there is another one, but we are only looking at this 1.30. So 0.0968. Okay. So that value will be, the probability of this will be 0.0968. So let's call it as 0.1. Okay. Similarly, the other case, the z is equal to, okay, x minus mu by sigma, where it is 75 minus 69 over 3. That is again 6 by 3, right? 69 plus 170, 5 plus 1, 6 by 3, which is 2. Okay. So the probability of 2 in this case is, we go back to the table and you find where is 2.0. This is the 2.0. Okay. 2.0 right here, 0.9772. Okay. So we get the value as 0.9772. So let's call it as 0.98 for this case. So the probability, resulting probability in this case is 0.98 minus 0.1, which is, we can call it as 0.88. So there is an 88% probability that a person, any given person, will fall between the height of 65 to 75 inches. Similarly, using the same approach, you can calculate the same for the 90. What is the height below which 95% of the US males will fall under? Okay. One way to solve this problem is, we go back to the table and we find out where is 0.95 is. Okay. So you can see that somewhere here you will get 0.95. So let's call this as 0.95. Okay, which is 1.65. Okay. Let's approximate it. Okay. So probability of z, less than or equal to 0.95 gives us as 1.65. Okay. So in this case, we can find that z is equal to x minus mu by sigma. So we just need to find what is x, because we know it is 1.65 is equal to x minus 69 by 3. 69 is the mean, it is this. So your x will be given by, x is equal to 69 plus 1.65 times 3. Okay. So then that you will get a value. That value is the value below, underneath which is 1.65 times 3 will be 15, 19, 4.93. So 69 plus 4.95 will be 73.95 inches. So 73.95 inches is the height at which, below which 95% of the American males should fall under. So using the same problem, same approach, we can keep on solving these problems for us. Okay. So I would request all of you guys to go through this normal distribution presentation and get yourself comfortable with the normal distribution tables, and more than that, learn how to use normal distribution under the Excel, so that you can use Excel to find the values of this. I mean, this is a quick lecture, because next thing you are going to learn soon is the hypothesis testing and the presumption of normal distribution and t-distribution and stuff like that. So this should help you to understand the applied side of normal distribution, why it is important that we take normal distribution, so that we can use parametric statistics, do inferential statistics, or testing of the hypothesis. Because testing of the hypothesis is the fundamental aspect of analytics. The difference between data mining and data analytics is that data analytics has a hypothesis, where data mining does not have a hypothesis, it just looks for inherent patterns in the data. With this, we will conclude today. Thank you very much, and we will see you in the next class. Thank you.